Hi, my name is Bardia Zandian, and I'm a PhD candidate in the Electrical Engineering Department at USC. Today I'm going to talk about improving processor life expectancy by runtime monitoring and mitigation of circuit wear-out. The problem we are facing is reduced expected lifetime of processors due to increased circuit wear-out, and the proposed solution is to do runtime wear-out monitoring and mitigation. Let's look at how wear-out manifests at different layers in the computer system stack. The root cause of wear-out is at device level, and it manifests in form of device timing degradation. This translates at the circuit level into gate timing degradations, and eventually at the microarchitecture level into path timing degradation, and eventually path timing violations. In the higher levels in the system stack, these translate into execution errors. We focus on the lower three layers and try to design cross-layer hardware solutions to deal with wear-out. Hence, we define wear-out as gradual timing degradation and eventual failure of circuits. The circuit wear-out problem has existed since the beginnings of integrated circuits, but it's becoming more severe. This is because the rate of wear-out is increasing with silicon scaling. This is caused by higher current densities, higher electric field stress, and higher operation temperatures, all of which are side effects of silicon scaling. Furthermore, it is hard to do design time prediction regarding the amount of wear-out the circuit is going to suffer from during its in-field operation. This is because of process variations and high unpredictability of runtime circuit utilization. In addition to these trends, we are also entering an era where there is a high demand for a longer lifetime of electronic circuits. An example of this would be implantable electronics or mission-critical control systems, where a life expectancy in the order of decades is now required. So we propose to monitor circuit wear-out during its in-field operation and then use this information regarding the wear-out state of the circuit to adjust its operation with the goal of increasing the chip's expected lifetime. How we achieve this is using a novel adaptive critical path testing framework. This testing approach is based on test vector injections, and each test injection is designed to not only measure the functional correctness of the circuit, but also measure its timing degradation. A test vector is a group of inputs to the circuit being tested, which are designed to sensitize and activate the most critical paths in the circuit. Each test is done at a test frequency which is slightly above the normal operation frequency of the circuit. This would allow us to detect critical levels of wear-out before they are severe enough to negatively impact the correct operation of the circuit. Furthermore, this type of testing allows us to check actual devices and interconnects which are used during the normal operation of the circuit. Therefore, the output of each test would give us an image of the exact amount of wear-out the devices have suffered from during their normal operation. Finally, here is how we envision a distributed network of monitoring units to be placed on a chip. In this example, you see a chip which is a multi-core processor, and you see multiple reliability monitoring units placed across different locations on this chip. And these monitoring units would provide us with an image of the wear-out state of this chip during its in-field operation, which then can be used to adjust operation of different parts of the chip and improve its life. Thank you.